Hello, everyone, and welcome to this online tech talk on securing your Amazon EKS cluster. My name is Pavan Mistry, and I'm a senior developer advocate with the AWS Container Services team. I worked at AWS previously as a specialist solutions architect in security and compliance and as a manager within AWS security. Prior to AWS, I've been a security consulting leader at global enterprises. In my current role, I work with AWS Container Services product and service teams to inform developers on container services features and conduct product deep dive for our customers. You can follow me on Twitter at 98 p.m. and feel free to contact me through email or on Twitter anytime for questions on AWS Container Services, container security, or AWS security in general. So this is a level 300 tech talk. So understanding of AWS and AWS security fundamentals and Amazon EKS is expected. So we assume that you're aware of and understand the AWS shared responsibility model. First, for context, we'll quickly understand the fundamentals around EKS security to set the tone for the presentation. Next, we'll do a deep dive into how authentication and authorization works in the context of AWS IAM and OIDC using a demo. And at the end, we'll learn of the EKS best practices for security and discuss resources you can refer to for Amazon EKS security controls. The goal of the tech talk is to leave you with an understanding of security controls within Amazon EKS and how you can improve security of your EKS clusters. These resources will help you make an informed decision to help secure your clusters and meet regulatory and compliance requirements for your EKS workloads. We'll end the tech talk with a Q&A session. So before we dive into the details about securing Amazon EKS, let's talk about the threat model in the context of actors and capabilities. So this is just a high-level concept of actors being the nouns in the situation. So this could be anything from application developers on a cluster, or a cluster administrator, or an AWS administrator, or this could be an application process on the node or EC2 instance. Or it could even be an anonymous user of your system accessing your website. And then the capabilities are the verbs. So this is the things that the nouns can do, like credentials access or network access, or things like system permissions or syscalls, or ability to time responses, which can get really tricky when you get into the cryptographic space. So the value of this model is it gets you to think, how can I try to minimize what capabilities can the actors use? Or what verbs can the nouns use? So these are just examples and not an exhaustive list, but it helps you start thinking about these things on the basis of your threat model. There are resources like the attack framework from MITRE that can help you with defining your threat model and go a bit deeper into this. So let's apply this to an Amazon EKS cluster. In this situation, we have an Amazon EKS cluster with the managed control plane that AWS offers. So we have VPC, we have EC2 instances in there that could be AWS managed nodes. And you also have the subnets and security groups in this VPC. The actors here are the pods running in your VPCs, which are processes running on the servers. You have application developers that have network and credentialed access to the Kubernetes cluster. You have cluster administrators who have network and credentialed access at different levels, and their network access in this case is over AWS Direct Connect, as you can see. And then you might have an external attacker or adversary that might have a different level of network access that's not credentialed over a load balancer. So it's restricted to specific ports and specific protocols. So as you look at your own application and draw a diagram like this, you can see the access patterns and start enumerating who can do what and how. So you can minimize the actors to do what they need, and that begins to form the basis of your threat model. And hence, there is no one-size-fits-all for security. So under the shared responsibility model, the security controls shown on this slide can be viewed as tools or configurations provided by Amazon EKS for your cluster security in the cloud. You may use these configurations and tools in your cluster in line with your threat model that we discussed earlier and your security and compliance requirements. So control plane logging. In EKS, when you create a cluster after creation, you're able to upload logs to your AWS CloudWatch logs. So the logs we offer from control plane are API server process logs, the controller manager in Kubernetes, the scheduler, the authenticator, and also the API audit logs. The API audit logs are well-formatted structured JSON and even include request response for which user made the call. It also includes IP address information and that sort of thing. Using CloudWatch log insights, you can actually query very quickly which users had 400s or unauthorized access. We'll look at this in a demo later where we raise 400s in the authentication flow. Another feature EKS offers is endpoint access. So by default, when you create an EKS cluster, the endpoint is public and it's on the internet. If you don't want that enabled, you can turn it off and just have Kubernetes API server be available in the VPC of your workers. Another feature that we offer is access control. So authentication control, so that when you talk to the Kubernetes cluster as a user, you are using your AWS IAM identity. So we basically give you the ability to say which AWS IAM users can access the EKS cluster. We'll dive into this a bit further shortly. So another feature that Amazon ECR, the Elastic Container Registry, provides is image scanning. So as an image gets pushed to ECR, it can be scanned and you can get notified about CVEs in the base OS and packages of your container images. Related to ECR and not listed in this slide is a core feature that we announced last year to encrypt the images in ECR using AWS KMS or Key Management System. So this allows you to meet any container image storage security and compliance requirements. I did a deep dive tech talk to explain this ECR feature last year, so I'll provide a link at the end of the presentation. And then a feature that EKS provides for pod security and service accounts is the IAM roles for service accounts, or IRSA. This allows you to assign IAM roles to specific pods through an annotation in the manifest. Secrets encryption for Kubernetes secrets allows encrypting Kubernetes secrets object within your cluster with AWS KMS, which is traditionally a base 64 encoded object. So this helps protect your application and cluster secrets with AWS KMS or AWS Cloud HSM. And again, I'll share a link at the end of the presentation to the deep dive talk I did last year on this topic. Last year, we also announced CIS EKS benchmark in July to help customers accurately assess the security configuration of Amazon EKS clusters, including security assessments for nodes to help meet security and compliance requirements. We offer assessment tooling through KubeBench, which is an open source tool from Aqua Security, who is an AWS partner. In addition to that, we also announced security groups for pods, which integrates Amazon EC2 security groups with Kubernetes pods. This means you can use Amazon EC2 security groups to define rules that allow inbound and outbound network traffic to and from pods that you deploy to nodes running on many Amazon EC2 instance types. I would like to mention a couple of security features that Fargate provides for customers using EKS on AWS Fargate. So Fargate offers ephemeral storage encryption to customers, pods, and workloads using industry standard AES 256 encryption. And for runtime security needs, Fargate also announced sysptrace capability to allow customers to trace syscalls and improve observability and security. I'll share a deep dive session we conducted on our Containers from the Couch weekly show on this topic at the end of the presentation. And more recently, we announced the OIDC Identity Provider Authentication. We introduced OpenID Connect, or OIDC Identity Provider integration with Amazon EKS, which allows customers to bring their existing users and user management workflows to new or existing Amazon EKS clusters. So let's deep dive into this feature now. So Amazon EKS uses IAM to provide authentication to your Kubernetes cluster. but it still relies on native Kubernetes role-based access control for authorization. This means that IAM is only used for authentication of valid IAM entities. All permissions for interacting with your Amazon EKS cluster's Kubernetes API is managed through the native Kubernetes RBAC system. When you create an Amazon EKS cluster, the IAM entity user or role that creates the cluster is automatically granted system masters group permissions in the cluster's RBAC configurations. This IAM entity does not appear in the config map or any other visible configuration. So to grant additional AWS users or roles the ability to interact with your clusters, you must edit the AWS auth config map within Kubernetes. The Kubernetes API integrates with AWS IAM Authenticator for Kubernetes using token authentication webhook, which is a Kubernetes feature. This works using the AWS SDS get caller identity API endpoint. This endpoint then returns information about whatever IAM credentials you use to connect to it. The authenticator client or kubectl that you'd use generates and pre-signs a request to the endpoint in the form of a token which passes through the Kubernetes authentication system. And the token is passed through the Kubernetes API server into the authenticate endpoint through a webhook configuration. So the authenticator server validates all the parameters of the pre-signed request to make sure nothing looks unusual, and then submits the request to SDS endpoint, which validates the client's HMAC signature and returns information about the about the user. Now that the server knows the AWS identity of the client, it then translates this identity into a Kubernetes user and group via a simple static mapping. So let's look at this action through a demo. Okay, so here we are in the terminal and we are listing the clusters in EKS. So we have one cluster within EKS OIDC test. And what I will do is call the get token API to get the token and against the cluster. So here's the token, and we use this token and find out what it's a base 64 encoded token. So we store it in a variable and then use that to decode the base 64 encoding, which will give us the actual SDS call to get caller identity. So it identifies the user who's calling the API, and it has the signature based on AWS SIGV4 signature algorithm. So that's the credential which is calling. So it has the included credential and the different parameters that are expected out of the SIGV4 request going out to the SDS endpoint. And that's the signature which is formed through the SIGV4 algorithm. So now that we understand the token, we are going to look at the endpoint through describe cluster and get the endpoint. So that's our public facing endpoint for the cluster. So that's where all the requests from the end users go to. So let me store that in the other window, that token, and then use that token to make a request to the endpoint. So I'll use a curl command, and you can see that I have it pointed with the token, the expected format, and then pointed to the public endpoint. And there you go. So you can see that I have successfully authenticated, and the API allows me to list all the endpoints that API server presents to an admin user. So if you're not an admin user, here I'm presenting myself as an admin user. If you're not an admin user with the Kubernetes RBAC, you'd have just a specific set of endpoints you'd have access to. So that's the end of the first demo. So this approach of authentication works well for customers with users already in AWS IAM. There are a few challenges to this approach of authentication. First, it requires your IAM user to assume a role that is mapped to an RBAC group or user in a static YAML file stored in the config map. And to assign rights to a user, you need to create the IAM user, create the IAM role that the user can impersonate, add the IAM role to the map roles element in the AWS auth config map and in the kube system namespace, create a Kubernetes RBAC role binding or cluster role binding that binds the user or group in the AWS auth config map. And all this is very error-prone process and difficult to automate. So we learn from your feedback, as you can see on the slide, on the containers roadmap, 330 of them actually, that if your organization has an existing identity management system, you'd prefer to use your own OIDC identity provider instead of using AWS IAM for Amazon EKS. Many development teams don't have administrative access to AWS and create an IAM user or role for each developer. And this can be time consuming, which cannot scale well. Hence, we launched OIDC Identity Provider Authentication for EKS that will dive a little bit deeper now. To accompany this feature launch, we wrote a blog post to introduce and explain this feature as well. So feel free to refer to this blog. All right, so OpenID Connect is an interoperable authentication protocol based on the OAuth 2.0 family of specifications. It adds a thin layer that sits on top of OAuth 2 that adds login and profile information about the identity who is logged in. You can use an existing public OIDC identity provider, or you can run your own identity provider. As shown in the diagram, the flow isn't hugely different from the AWS IAM flow we looked at earlier. Here, the user authenticates with the IDP first, and on successful authentication, the IDP issues an ID token, which is presented to the API server endpoint. That then authenticates the user provided token for validation and then authorizes the user to the API. So let's jump into a demo again quickly to understand this a bit deeper. All right, so here we have a CDK code which we have generated. It's detailed in the blog post as well. So it's just a code to create an IDP using AWS Cognito, which allows you to create an OIDC compliant IDP. And what we're doing is just building a user pool which allows you to store users. So here we have the client ID, the issuer URL, and the pool ID generated within Cognito using AWS CDK. And the reason we do this is it's easier than interacting with the console and selecting all the different options that the console presents for AWS Cognito. So there are 3 parameters needed, and we will use these parameters to create a user and add the user into a group. So here we are just setting a password and creating a group within the user pool, Cognito user pool. And as you can see on the console, we now have that user pool created with the particular user that we set up. And the instructions for these are all in the blog post if you want to follow along. So here that user test@example.com is attached to the secret reader group, which means we want that user to just access the secrets. And we have a domain set up as well, so that you can use this domain for the authentication requests in your flow. And then if you look into the app client settings, you'd find the hosted UI, which we can use to mimic an application or a user sign-in. So it has a pre-built page that Cognito offers, and all we need to do is enter the username, the email that we use tested at example.com, and the password which we have set in the previous steps. And the way the IDP works within Cognito is once we sign in, and that's an expected behavior, is we get a token or ID token particularly. It provides an ID token and an access token as a response. So once the user authenticates successfully, these are the two tokens that are returned by the IDP. So that's the beauty of standards. With the OIDC standards, this should be an expected behavior for any IDP provider. So let's take a look at those ID token a bit deeper into what they consist of to get an understanding. So here, as you can see, they're delimited. There are two tokens returned. One is the ID token and the access token. We're interested in the ID token because that has valuable information to set up our OIDC in Amazon EKS. So right now we are taking the payload, which is delimited by a period. So taking the payload that's between the two periods within the ID token, and then using that to store it within a variable. So that's our payload, and that has the key information. This is all JOTS or web token format, so you can look at any of the web token decoder, JWT decoder, and it will give you the details. So once we base64 decode that payload, it will show us the contents, and if we actually pass it through JQ, then it gives us a well-formatted content. And we can see here that the groups key value store is marked, the key is the Cognito groups, and that identifies our group name, which is secret reader. We'll use that information to input within our configuration. So this is important because every IDP might have a different way of sharing the group details. So in this case, we'll look at our configuration, existing cluster, and go into configuration and authentication. That's where you configure or associate your identity provider. So these are the new sections added within your configuration UI for the console. And here you can input the name of your identity provider. And now I'm adding the groups claim, which was Cognito groups, which we noticed in the token. And advanced options, there's some prefixes you can add and add more claims if you need. Here we'll add the groups prefix as GID, which is the expected prefix we expect from the token, and then associate. So within like 15 or 20 minutes, you would have the association ready. So I'll quickly run through this and show you once the association is ready. So right now it's creating and updating and doing all that's needed behind the scenes. And once it's completed, we'll see that all the details are there, and you'll be able to use that OIDC identity provider. So now that it's ready, you can see the status is active, and you can do this through a CLI as well. So there is a new API which has been added to associate identity provider through CLI if you wish to. But now that the association's up and running, let's go back to Cognito and to our user pool to get a fresh ID token. I think it was in the app client settings, the UI. So we go back to the hosted UI and sign in again to get the ID token. And we can copy this into and extract our ID token from this, separated from the access token, and store it in a variable. There is other ways to get the ID token through CLI options that Cognito provide, which is described in the blog. So take a look if you're interested in doing that. But here we are just storing the ID token into a variable so that we can use it and confirming that that's the expected token. Right, now that we have the token within the variable, we'll try and authenticate again with the endpoint. So I'm looking for the endpoint URL using the AWS EKS describe cluster command. So there we go, we have the endpoint details. And now I can use the previously used curl command to replace that IAM token format with an ID token. So we're using the new ID token, but here we're getting unauthorized. So it's not letting us authorize, we're getting 401, but because it's not the expected format, so it doesn't need that particular header in terms of the authorization bearer token. And yeah, once we do that, we are forbidden. So that's really interesting because the code we get is 403, which means we were authenticated, but not authorized to access the endpoint. And the reason why is because when the endpoint sees the user and they don't see what RBAC permissions they have, that's when it throws this error and says, oh, I can see who you are, but I cannot find where you're going. So hold on a second. So that's where this 403 is happening. So we need that RBAC. We need to set up the RBAC permissions through role binding and cluster role. So that's what we'll do now. Is we'll create a role binding and cluster role for this particular user, and for actually this particular group rather than a user, because that's the best practice where it's not scalable to add individual users, and it's a good practice to add groups rather than a user in your role binding. So that's what we'll do now. So create a new file, and here we are just using a cluster role object, which we'll save as cluster role for secrets reader. And then apply this to our cluster. So here we have a cluster role created to read secrets. And now we'll create a role binding to attach this role to the group that we have created in Cognito. More importantly, you'd have the cluster role binding include expected prefixes or claims prefixes that we had. So it's interesting to note here that you have the kind group, and within that group you have the prefix or the and the group details which are expected. So once we create and apply that role binding, that means now the request coming in from the user should be authorized in terms of accessing the secrets. So let's try and do this here. So kubectl has a useful parameter to allow passing on tokens directly. So what we'll do is use that -- token to allow you to pass those parameters and call secrets objects. So when I do that, the request is successful, as you can see. So you can list all the tokens or all the secrets within the cluster. One thing you may want to try is get nodes. So you may want to get nodes, and hopefully that would fail because the object or the user doesn't have access to any other object than secrets. So that's the end of this demo, and hopefully that gives you a bit more detail around the operations of OIDC integration with Amazon EKS. Okay, so as discussed earlier in the EKS security control slide, OIDC user access is monitored through audit logs available through CloudWatch logs. And you can also restrict which OIDC identity provider can be attached to your EKS cluster, and whether an admin can attach the provider or the identity provider to the cluster through IAM policies. These are very interesting controls. One is a preventative control and one is a detective control on the OIDC integrations to monitor and control your OIDC integration. So referring to the shared responsibility model for your security in the cloud needs, where you own the security and compliance responsibilities for your EKS clusters, we launched EKS Security Best Practice Guide last year. And it's an open source project which is available on GitHub, where we provide recommendation on good practices to secure your clusters. So in the next few slides, we'll take a look at some of the recommendations that the EKS best practices provides. So this is publicly accessible, and you can contribute to it if you'd like. It's on GitHub, and it provides a list of security guidelines, best practices, and recommendations. So first thing that we recommend doing here is scan container images, and there are a lot of really good open source solutions for doing this, including Claire, Trivy, and Anchor. And we actually use Claire as part of ECR's scan on push feature. So ECR is the Elastic Container Registry, and you can scan an image on push or on demand. But beyond that, it's always a good idea to create a slim image with a slim base layer. Another recommendation is to defang your images, and you can do this by removing files with the set UID or set GID bits from the image to prevent escalation of privileges. It's also important to run your application as non-root user, and you can do this by adding the user declaration to your Docker file. Lastly, you want to use the endpoint policies with the Elastic Container Registry, because there is an attack vector where you can package data in an image and push it to another ECR registry in a different account. So by using the endpoint policy, you can restrict which accounts the images can be pushed to. All right, so when it comes to network security, it's really important to realize that by default, all traffic between pods within a cluster is allowed. So we recommend restricting that traffic, and to do so, you can make use of a network policy. So network policies are great to restrict east-west traffic within the cluster or between applications, and they can be used even for north-south traffic. So when you run Kubernetes within AWS, you can use security groups, but you can still use network policies for north-south. So when you do use network policies, we recommend beginning with a deny all global policy, and then you can add port 53 or DNS egress to the kube system namespace for service discovery to allow traffic into kube system. And then you can also allow traffic within a namespace if required. It's a good idea to restrict outbound traffic that doesn't need to connect with external services. However, if you do have applications running in the cluster that have to communicate with services outside of the cluster, you can implement controls through Cilium, which is another network CNI that has support for layer 7 policies. Another option available is to assign security groups to your pods. And so with that, you'll be able to control the traffic between services within cluster and services within your VPC. Finally, we recommend using encryption between service-to-service traffic using a service mesh like App Mesh. For runtime security, we recommend using admission controller-based solutions like OPA, Kyverno, or Gatekeeper. And you can implement the following runtime security measures that include things like denying privilege escalation, running as root, or denying mounting host path, and dropping Linux capabilities. And these are really considered table stakes, and they help you mitigate the risk of an attacker escaping the confines of a pod or a container and getting access to the host. If you require additional controls, you can add AppArmor or SecCom profiles. And there are a lot of really good third-party options from our partners like Aqua Security, Twistlock, Sysdig, and StackRox. So all of these providers feature services for runtime security. Okay, so to cover the Amazon EKS security controls, we have guidance around, deep dive guidance around each of these topics. So rather than cover each of them in this presentation for the scope of this presentation and the content, I have listed them in this slide so you can deep dive into them. So for control plane logging, we have the official docs on helping you how to enable them. With endpoint access, again, we have guidance around restricting endpoint access to private endpoints if you require to do so. Authentication controls, we have guidance around that as well. With ECR image scanning and ECR encryption, we have great tech talks. For IAM roles and service accounts, IRSA, we also have some details there with some sessions we did on containers from the couch, our weekly show. For secrets encryption, there is a tech talk I did, which you may find useful in terms of deep dive into how encryption works within EKS. We covered security groups for pods through an example of WordPress in AWS EKS, in Amazon EKS, and for OIDC, things that we covered today and the blog post provide enough information. But if you have anything else which you would like, please give us feedback through the roadmap, or you can contact me and I can help you out in your integration with the OIDC IDP. For Fargate runtime security, we did a deep dive demo on CFTC, our containers from the couch show, and same for OPA admission controller if you'd like to look into those options for securing your Amazon EKS clusters. So to recap, we looked at the Amazon EKS security primitives and the EKS controls which are available. We looked at the deep dive into authentication and authorization using AWS IAM and OIDC, and also looked at the best practices which are available for free for you to access on security. So thank you very much for attending this session, and hopefully it provided you information around how to secure your applications and containers running on Amazon EKS. And I'll open up the session for any Q&A questions you may have. So thank you very much for attending.